And for now, I want to introduce our next speaker, who's Francesca Chiappini. She works for the CITC, which already was mentioned by Jeroen. They're very devoted to power electronics and so-called chip packaging. Francesca, please come over. We'll give the remote to you. And I think very interesting to hear also like applications maybe for people in the automotive industry, 5G communication specialists who could be in the audience. So please give us an update on it.
Thank you. Good afternoon, everyone. My name is Francesca Chiappini. I represent here the Chip Integration Technology Center, CITC. I'm very happy to be here and to present our organization for the first time in Japan. And so I would like to thank the organizer for giving me this fantastic opportunity to show you our work. With my talk today, I would cover most of our activities in the domain of semiconductor and photonics packaging. We work on enabling packaging technologies in the field for RF application, power electronics, and photonics. But first, a brief introduction about our organization. So CITC, the same way as whole center that Jeroen presented earlier, is a joint innovation center. We are quite a young organization. We were founded in 2019 on initiative of local semiconductor company that pushed to have, again, a research center specific on packaging technologies based in the Netherlands. Our technical staff comes from two major organizations in the Netherlands, so TNO, that we heard a lot of today, of their work, and the Technical University of Delft. And we are located in Nijmegen. So what we do, we really develop new technologies for semiconductor and photonics packaging. So we do that together with companies. So we work in an ecosystem type of model where we accelerate innovation around four main application areas: power electronics, RF and millimeter wave, advanced and additive manufacturing packaging, and finally, of course, photonics. We're also active in trainings and education programs because we know that skilled personnel for companies is very scarce in this field. So we work also with schools and training institutions at different levels. This is a nice picture of the campus where we are located. This location, it's a heritage of the old Philips semiconductor work, which now has split up in the different companies like NXP, Amplion, and Xperia that are sharing the site with us, together with many innovative companies. We have our own lab facilities, our own infrastructures, and through our work, we collaborate with partners across the whole semiconductor chain, from device manufacturer to system integrators, material suppliers, and equipment suppliers, and of course, our knowledge partners like the technical universities, Whole Center, TNO, and PITC. So what do we actually do in our work and what we can offer to partners and companies? Well, the first and foremost is access to innovation. So we do research and development for companies and together with companies that we work in our 2 to 5 years research programs together with industrial partners. Next to it, we also have quite a broad lab infrastructure, including a full back-end assembly line and clean room processing. And we also make that infrastructure available to our partners either through direct collaboration with us or with resident engineers that can come and join our facilities and learn also from our way of working and get access to our know-how. And the final point is about education, where we offer several trainings for each level of school and also to professionals. And now I will use the rest of my talk to go into details and detail about the 4 research line and explain what is that we do and what is it our vision for the future for those application domain in packaging. Let's start from what we call thermal high performance packaging. In this program, the main application domain, it's power discrete. So we work with this type of components that do not present the extreme I/O count, but the I/O count is quite small. But they present several challenges when it comes to reliability and power dissipation. Especially from legislation, there's the challenge, of course, to remove all lead-based materials from electronics. So in this case, we focus on the development of technologies to make a reliable die-attach connection completely lead-free. And of course, we are very well aware about the challenges that the CTE mismatch between the silicon and the copper bring. So we're developing an innovative die-attach solution to tackle this challenge and make sure that these devices can, for instance, survive the very demanding reliability quality tests from automotive. How we're going to do that? Well, we have a technology roadmap that we divided in 4 main steps. And the first two, point 1 and point 2, is actually supporting and improving the state of the art. So this type of devices, they all work with wire bond, die-attach solution, and then wire bond of clip attach. And we help companies to screen and improve on die-attach materials to make sure that they can meet the reliability requirements. But the next step is really looking ahead. So how will this type of products look like 10 years from now? And in that sense, I will come to this later, we have a roadmap to use additive manufacturing technologies to build the package in a way that it will not require any longer the use of die-attach materials, removing the problem of die-attach reliability in one go. So for the state-of-the-art type of technologies, and this is a very good example to show you how we work with functional test vehicles. In this case, we use packages that are PQFNs. It means that we can do the whole packaging process in our labs. We go from the naked die to the complete device. And our expertise is to optimize the die-attach process to assure that we can pass reliability testing. After that, we do characterizations. So we can do electrical testing, mechanical testing, different kind of process control with confocal microscopy or CSAM measurements, cross-sections, to really not, because from reliability tests, we don't want just to get an answer, does it work or does it fail? We want also to understand when it fails, why it fails, such that we can also improve that in the future and tackle those problems. The next application domain that I would like to talk about is for RF and millimeter wave. This is a very important topic at the moment because it addresses application domain like communication, 5G, beyond 5G and 6G, and automotive radar. So if we look at the trend for this type of products, we see an increasing trend of frequencies, of operating frequencies. So the 5G that we will have, or we have on our mobile phones, this operates between 28 and 39 gigahertz for the high frequency bands. The automotive radar now works at 77 gigahertz, but we know already that 10 years from now, 6G will come, and this will operate at much higher frequency, 100 gigahertz. Automotive radar, 140 gigahertz. And this scaling with frequency actually has huge consequences on the form factor of the devices itself, and also then on the packaging technologies. So you can see here an example of what is commercially available for a 77 gigahertz radar, a product from NXP, where you have an antenna on board type of concept, so a big RFIC chip on the board and the antennas on the side. And actually, the trend is to go to a more integrated structures, like the sketch on the right side on the left side, sorry, of the slide, with an antenna in package, with an antenna array integrated directly in the package. Well, to get there is actually quite challenging because you have this type of devices brings two main challenges with themselves. One is the need to reduce the losses. at high frequency. And the second one is that you have a very complex RF design, you can imagine, of an antenna array in a tiny electronic packages. So if you have to make it with current technologies, you will not be able to achieve the right performance. Especially because there are several challenges that I've listed here, but the main ones are that you really need to make complex multi-layer structures of dielectric and metallization. And depending on the layer and on the function of the layers, the thickness of these layers might vary from few microns to hundreds of microns. So you need to have a range of technologies that cover this broad range of thicknesses. And of course, all the materials need to have the right permittivities and, more importantly, very low dielectric losses. So our technology roadmap for this type of products is actually, we are developing a technology platform for cost-effective millimeter wave packaging solutions that is based on fan-out technologies that are scalable to panel-level production. The reason why we chose for this technology, for a fan-out type of technologies, it's because it assures the lowest and the shortest possible path from the IC to the RF part, so the shortest possible interconnect, which is crucial to keep the losses in check and to have low losses. So how we're going to do that? First, we start from the redistribution layer. So actually, the interface from the main board of the system and the package itself. These are usually quite thin layers, and they need to have the characteristic of being extremely low losses, assure high isolation of the millimeter wave systems. The second part is what we called a 3D fan-out package. As I showed you before, these RF packages will be extremely complex, even with an antenna array system included. So for that, you really need to utilize the whole volume of the package for functionality. So the package, it's no longer only protection for the IC, but is really a functional part of the device itself. And through the package, you can achieve more performance for your device. So this means that you need to have interconnect that go through the volume of the package and that can connect to the antenna system to the bottom part of the package. And then finally, you can have the full functionality of the package, and even looking at the future with this type of technologies, integrate to what we call the millimeter wave module with different components in the same system. So how are we doing this? This shows also this work that we have really nice clean room capabilities for processing to enable us to make first redistribution layers, and then what is very important here is high aspect ratio interconnect. So for the millimeter wave redistribution layers, we're making thin layers of dielectric and metallization. Metallization is done with semi-additive plating, so we can achieve high resolution down to more or less 10 micron line spacing. And we can achieve thickness of metals between 5 and 10 microns, which is good enough for this type of application to have low losses in the metal layer. The second building block of the technologies is actually the interconnect. Now, I told you before that we will need to bridge layers of hundreds of microns of thickness in this type of packages, and this calls for high aspect ratio interconnect. So interconnect that are very long and extremely narrow to be able to integrate all the functionality of the package in the package itself. One of the ways we are approaching this problem is by a technology that is called the true polymer via technology. We didn't invent that, but actually we are trying to bring this technology to a higher level of maturity from a university scale type of experiment to industrial production. So for this type of interconnect, the approach is different than the conventional interconnects, in a sense that normally to make a via, you take a substrate, you drill a hole, and you fill the hole with metallization. Now this brings intrinsic limitation to the aspect ratio that you can achieve. So we do it the other way around. We first build a pillar with lithography means, so it means that we can do it very precisely and of the shape that we want. We then metallize this part, with plated copper, so very good quality metal for RF signals, and then we embed this in encapsulation materials. And here you see in this picture a nice examples of these metallized pillars with copper conformal coating on these pillars. So with this technology, actually, we are working on different technology building blocks to enable this type of packages in the future. And it shows in our roadmap how we're going to do that. The third topic we're working on is actually specific on a family of technology from additive manufacturing. And for this topic, we are collaborating closely to our sister institute, Whole Center. So we make use of their expertise and their know-how in these additive manufacturing technologies, but then for a different application domain, so not printed electronics, but advanced packaging. And the first use case for this type of technology, we started with the packaging for vertical devices. So actually what I told you at the beginning, so the lid frame, state-of-the-art type of packaging, well, our plan here is actually to revolutionize this field, and actually remove the need of a lid frame altogether. So the state-of-the-art is the traditional package for discrete components. But currently, there are some examples already out there of what is called beyond state-of-the-art, where actually it's a panel-level type of processing that has that you don't start with a lead frame, doesn't have any wire bonding. And this type of panel-level processing actually offers great advantages from a performance point of view. You reduce the package performance dramatically if you use this type of packaging with respect to state-of-the-art technologies. And you can also, it's very attractive because you can manufacture instead of strip-based on large panel-based. However, that type of process still includes serial manufacturing of the drilling of the vias and of the stud bumps of to connect to the top side of the die. Now, these processes actually, because they are serial and they're slow, they actually accounts for the biggest portion of the cost of the package. And actually, they make this solution, that is from a performance point of view very attractive, from a cost point of view is actually almost prohibitive. So our idea here is actually to move to a different solution where we still keep the benefits in performance of the panel level type of manufacturing, but we replace this serial type of processing with parallel additive manufacturing processes. So we get to something that we call a printed package. Our technology roadmap is actually to start from the state-of-the-art, learning from what Whole Center has done on the field of hybrid printed electronics, and then build upon that and transfer those processes actually to the chip manufacturing. What we're doing now, where we are, is actually in point 2. We are demonstrating the different building blocks of this technology, and our aim is to get to a fully printed package soon, and then show that this technology is ready for scale-up and reliability. An example of what we're doing, normally in semiconductor manufacturing, the encapsulation, the epoxy molding compound, is actually done through a molding process, either compression or transfer molding. We do it differently. We print it. There are some material suppliers that offer already this type of process of materials. And the advantage of printing is that, of course, you can already print large panels, but also, if you are very skilled in printing, you can also make vias. And this is what you see here in the middle, is that we are able to print vias on top of the die itself. And this means that we don't have to drill vias any longer. So we effectively replace that, that process that is slow and expensive by a parallel process that is quick and cheap. Via printing will have for sure some resolution limitation. You cannot just shrink the via and go to very high resolution indefinitely. So we are also thinking of other technologies to make this interconnect. So we are also talking to the startup company Phonontech that we'll talk later to also make kind of printed stud bumps instead of then made with a wire bonder. And the final part is then how do we bring metallization? We're still talking about power devices, so we still need to have metallization with good electrical and thermal conductivity. Our solution here is what we call additive plating. So instead of sputter a seed layer, do lithography, and then etch back, grow copper with copper plating, and then etch back to the seed layer, we do replace this process by printing a seed layer, by printing technologies again, and then we do electroplating. And then here you see an example of already some experiments that we perform showing the feasibility of this approach. Now, I will use the last minutes of my presentation to address the final application domain that I want to talk to you about today. And this is packaging for integrated photonics. So photonics is a very promising field, and especially in the Netherlands, there are a lot of investments in this field. And it requires, from a packaging perspective, a bit of a different approach. So today, which is what state of the art is about, we can do photonics assembly. We do it through customer project. And we do it with what is called a classic assembly and packaging technologies. So each and every assembly is done one by one, each of them connected to an optical fiber at an early stage of the processing. So this is absolutely not a sustainable way of producing, and this also accounts for the fact that from a photonics device, 80% of the cost is in the packaging and 20% in the photonics chip, while for the semiconductor world is exactly the other way around. Most of the cost is in the IC and not in the package. The way to bring down the cost in photonics packaging is actually being able to move away from the single device manufacturing one by one to a more parallel type of processing. So actually, what my colleagues call it, go from a photonics approach to a semiconductor approach to the packaging process. Currently, in the photonics world, there are a lot of startups working on it. The assembly costs are very high, and there is the need to address hybrid and heterogeneous integration, and also find a way to integrate the optical fiber at the end of the manufacturing process instead of at the beginning of it. So to tackle these challenges, we also developed our roadmap for photonics integration, with our final goal is actually to semiconductorize the integrated photonics world and use technologies that are standard, that are scalable, that are cheap for the semiconductor manufacturing, and import them to the photonic world. We start from our state of the art. It is what we are doing now, and we support our many companies producing assembly for them. We are moving into volume manufacturing, so going from single device to strip level assembly, that for photonics is already a big step. And then our roadmap is to go to panel level integration of photonics devices. This is an example of a type of an photonics assembly, how it is done now. So you can imagine you see the photonics chip in the middle and then the optical fibers coming out of it. This demonstrates what I was telling you, that indeed all the assembly is done by one device per device, which is not doable to bring down the prices. The next step that we are working on is actually the strip level assembly. Here we use a packaging platform from the company RGR with a type of a liquid crystal polymer casing. And in this way, we can already reduce significantly the price of the assembly. But actually, our main goal, and all the subsidies that in the Netherlands are given for photonics development, are actually, we are going to use them to develop this concept. This is what we call a moonshot. So it's really looking far beyond what is possible now and find solution for big problems in this field. The need, it's clear, we need scalable technologies for photonics assembly. And we define this moonshot to move beyond what is possible now with photonics technology. How it works, in a few words, instead of for the die itself, we will go to flip chip integration instead of wire bonding. And through this process, we can directly connect to an integrated waveguide substrate. In parallel to that, we will also integrate pluggable optics to make sure that the optical fiber is then placed at the end of the production process. All of these technologies in the semiconductor domain are already panel-level type of technologies, so we want to use the same type of technologies for photonics integration. So this brings me to the conclusion of my talk. I was very happy to be able to present to you our institute and show you what we can do for photonics and electronics packaging. We work in an ecosystem way of working, so we are open to collaborate with many different companies in this field, whether they are materials suppliers, equipment manufacturers, or device manufacturers. And with this, I would like to thank you for your attention. And if you have some question also in the future, you can reach out to me. Thank you very much.
Well, thank you, Francesca. To ask you one question,
yes.
What is like the next big challenge you're facing? And what could potential Japanese companies could contribute to it?
Well, depending on the application domain, there are different challenges. I think the common denominators of all our challenges is actually find the right materials for the right applications. So depending on the application, of course, you might need materials with high thermal conductivity for power, or with low losses for a ref, or also with low optical losses for waveguides for photonics. Many different challenges, but the key of all is actually having good materials that we can use. So I think all the material companies in Japan could play a big role in this.
And you have some over here.
Yeah, perfect.
Yeah. Thank you for that.
Thank you very much.
Yeah.